This problem of BMO Round 1 2021-2022 can be solved with these two ideas, considering small example and considering most restricted case. And also this problem of AMC 12A Spring 2021 can be solved with similar idea, and I will leave it as homework. You can try this one. So let's see how we can apply considering small example. The first approach, I can say one of the most useful things. And then during the solution, we have to use most restricted case. So let's read the problem. It says, okay, and if you had question about solving this homework, how to solve with these two ideas, feel free to send message my WhatsApp number in the description and comments. Also, if you wanted to learn more ideas and solve more related problems. Okay, problem 6. Marvin has been tasked with writing down every list of integers with the following properties. First property, the list contains 71 terms. Second one, the first term is 1. Third condition, every term after the first is equal to either the previous term or the sum of all previous terms. When Marvin is finished, how many of the lists will have a sum equal to 999999? So let's first check this number 969s. It's multiple of 9, so we can write 9 times 6 ones. And here, when you have 6 ones, you can say it's multiple of 1001. Why? Because look, it is 9 times 111000 plus 111. So if you factor from 111, it will be 1000 plus 1. So it will be 9 times 1000 times 111 times, here we factor from 111, and it will be 1001. So now if you prime factorize again, 111 is 3 times 37 and 1001. Prime factorization of this number is important, and it is so much useful when you want to calculate, for example, remainder when divided by 13, or for example 7. Now let's consider it will be what? It will be 3 cubed, this one, times 7 times 11 times 13 times 37. Okay, 7, 11, 13, 37. Now let's check the sequences. For example, it says the sum should be 6 nines, and we said, okay, 6 nines equal to 3 cubed times 7 times 11 times 13 times 37. Now we want to check a small examples. It says first term is 1 and each term is equal to either the previous term or the sum of all previous terms. So let's not consider this the first condition. Only we focus on condition 2 and 3. So let's check. For example, suppose it says the sum equal to 3 instead of this big number. If it is equal to 3, let's see how many good sequences are there. 1, 1. The second term always equal to 1. Because sum of previous terms or previous term, both of them equal to 1. Now, next term is 2 or 1. If it is 2, the sum will be 4. So it is 1. So we have only one sequence here. For sum equal to 3. Now, let's check sum, for example, equal to 7. So it will be 1, 1, 1. Here we cannot. Let me tell you something. For example, if here I say 2, then what happens? After that, all numbers are multiple of 2. Why? Because for next term, if we select previous one, it will be 2. If we select all previous ones, sum of them equal to 4. So if we select, for example, 2 here, then the sum will be multiple of 2. Like what? For example, suppose here, if we select sum of previous terms equal to A. After that, this sum is multiple of a divides this. After that, all terms will be multiple of a because next one. It is previous one or sum of all previous one. It will be multiple of a. It is ak. Again, previous one or sum of all previous one because a divides this part, multiple of a plus multiple of a ak prime. And so on. So we understand that when we want to reach sum 7, we cannot use 2 because then sum will be multiple of 2, but we know 7 is not multiple of 2. And because 7 is a prime number, so the only possible case is that we have 1, 2, 3, 4, 5, 6, 7. Only these 7 ones. Now we've understood that if you have a prime, the only possible sequence, if for example, if sum equal to p, that p is prime, we should have p ones. Now let's consider, for example, sum equal to 3 times 7, which is 21. So one case is that we have 21 ones. What is the other way? We said if we reach, for example, here, and we consider sum of previous term a, previous terms equal to a, then sum will be multiple of a. So the only possible case that we can do that is 1, 1, 1, 3, because 3 is a divisor of 21. 21 should be multiple of that, or we can say 3, 4, 5, 6, 7. 7 ones and 7, okay? Then in this case, the next term, which some of them should be 21. Next term is 14 or 7. The only possible case is 7 to be 21. Now here. The next one is 6, but 21. 6 is not divisor of 21, or 21 is not multiple of that. Because of this reason, we said so it is 3. 3, it has to be 3, previous term. Here it is 9. It cannot be 9 because 9 is not divisor of that. Again, it should be 3. 12. Again, 12 is not divisor. 15, 15 not divisor. 18 and 21. So we have only these 3 sequences, okay, for 3 times 7. Now let's check, for example, sum equal to 3 squared, power of a prime. This strategy that working on primes is so much useful. For example, p cubed, p squared, p to the power of something. It was also useful in SUMA Stanford problem. So for 3 squared 9, one way is that we have 9 ones. If we don't consider sum, if we consider sum, for example, 1, 1, 1, we can use 3. And then here we can say again 3, the only possible case. And it will be 9, and we have only these 2 cases, okay? Now let's consider, for example, let's work a bit on the our main number 6 nines, which was 3 cubed times 7 times 11 times 13 times 37. Now I say, suppose we have some number of ones. Then, for example, we consider sum. It is x1, and then we have x1 here. Suppose we have x1, x1. Some number of x1, then we want to consider sum of them. I consider it is x2 minus 1. Why? Because to have a good form. Because if here we consider, these are the places that we consider sum. Sum of the previous terms equal to, here we have 1x1 and these x1s. So I consider here x2 minus 1. So by this x1, x2 x1. So sum will be x1, x2. Again, suppose we have some number of x1, x2. Suppose there are x3 minus 1. Because sum of these part is equal to x1, x2. Because here we said x1, x2. And x3 minus 1, x1, x2. So how many x1, x3 in all? X3. So x1, x2, x3. Here we consider sum. Similarly, we continue x3 and here x4 minus 1 up to at the end. Suppose we have, let me minimize this part. For example, we have x1, x2 to xk, some number of x1, x2 to xk. It's the last number that we have. How many of these numbers we have? It is the first one that we have the sum. Suppose it is, we call it xk plus 1 minus 1. And there are at least one. It is here we have at least one, at least one, at least one. Let's erase this part. X2 minus 1 is at least 1, the number of these terms, because if they are 0, we don't consider them. And x1 is at least 2. We have at least two ones, because the first two elements, by assumption of the problem, the first one is 1, and second one can only be 1. Because sum of previous terms equal to 1, and previous term also equal to 1. So we have this. Now, sum equal to what? Equal to xk plus 1 minus 1 this term, and here we have x1 to xk, sum of them. So similarly, as we said, it will be what? It will be x1, x2, x3 to xk plus 1. It is equal to what? The sum. 3 cubed times 7 times 11 times 13 times 37. How many terms are there? We have 71 terms. 71 equal to x1 here. 71 elements we should have, plus x2 minus 1 plus x3 minus 1 to xk plus 1 minus 1. Okay, and we know all it is at least 2. All these terms are at least 1. Now, I know what? I know that, for example, here we have 37, and one of these xi's are multiple of 37. So, can xi be 37 times something? Is it possible? For example, suppose if xi1 is multiple of 37, because the product here equal to this. So, for example, if it is equal to 37 times 3, then it will be what? 111. Okay, 3 times 7, 21, this. And we know xi1 minus 1 here, xi1 minus 1 is 110. 100, one of them is 110 plus some other terms, some other positive terms, equal to 71. So that's a contradiction. If you multiply 3 by that, it will be so much large. If you multiply a larger number, it will be worse. So we should have 1xi1 that equal to exactly 37. Okay? So xi1 is, for example, here, or for example, we can say the first one is 37. It is not important. At least we can subtract 71, 36 from that. If it is here, you can subtract 37. If it is here, you can subtract 36 to see what is left, at least what is left. So 4 to 40, 34, 35 is left. Okay? Now here, some of the number of elements was 71 here. Now what numbers are left? We've considered. For 13, we can say the same thing. Because 3 times 13 is what? 39. Also, if you subtract by 1, 38. It will be greater than the number that is left. So, we cannot multiply 13 by a number, so there exists xi2 that is equal to 13. What is left? 35. We subtract it by 12. Because at least we should subtract 12 from the one number that is left. 35 minus 12 is 23. So we consider this. Now 11. If you multiply by 11, it will be 33. And if you subtract 1 from that, it will be 32, greater than the number that is left. So we cannot multiply 11 by a number. So there exists xi3 that is equal to exactly 11. 23 minus what is left, at least 11 minus 1, 10. 23 minus 10 is 13. If you have question about any part, as I said before, feel free to send message on my WhatsApp number in the description comments. So we've considered 11, we've subtracted 10, 13 is left. Again, for 7, if you have 7, for example, times 3, it will be 21. If you subtract 120, it will be greater than 13, but 13 is left. So we cannot multiply 7 by a number. So there exists xi4 equal to 7. We subtract 13, 6 from 13. 7 is left. Now 3 cubed, we have 3 cubed here. If you consider, for example, 3 squared or 3 cubed, for example, 3 squared, 9. 9 minus 1, 8 will be greater than this. So there exists xi5 that is equal to exactly 3. So 7 minus 2 is what? Is 5. Again, by same proof, there exists xi6 that is equal to 3. 5 minus 2 equal to 3. And last number, xi7 also equal to 3. But here we don't need to subtract 1 because it is one number. There exists one number that doesn't have minus 1. So here we consider 3 and 3 minus 3 is 0. And it will be okay. So we understand that if xi to xk, we have 3 times 3 times 3 times 7 times 11 times 13 times 37. So without loss of generality, we can say it is x1, x2, x3, x4, x5, x6 can be equal to this x7. And we can consider all permutations. For example, 37 here, 3 here, 7 here, 13, 3 here again, 11 here, and 3 again. Again, it is a good example. So we should see all arrangements. How many arrangements do we have for these 7 numbers? You can solve it with permutations, with repetitions. We say 7 factorial over, because we have 3 threes, 3 factorial, or we can say we have 7 places, 7 choose 3. We place 3 threes, then the rest will be 4 factorial, and they are same. So if we subtract, if we simplify, 3 factorial, 4, 5, 6, 7 will be left. 4 times 5, 20. 20 times 6, 120, times 7 will be 840. Okay, so the answer will be 840. Now, by this prime factorization that we solve this problem, we can also try this homework and try to consider special cases, small examples, primes first, and so on, and you can solve this problem. If you had question about the problem we solved or this homework, or wanted to learn 40, 50 important ideas in each topic, combinatorics, geometry, algebra, number theory, feel free to send message to my WhatsApp number in the description and comments.